So when we're talking about radiation and nuclear reactions, we want to be able to describe them. And to do that, we have three basic types of radiation that we're going to discuss in class. And the three types, let me find my black marker here. The three types actually go by the names of alpha, beta, and gamma. Alpha being the first letter, second letter, and third letter of the Greek alphabet. It's the most boring labeling system ever. But this is the three types of radiation that we're going to talk about. There's a few other rarer ones, but we're not going to worry about them in terms of this class or anything. We'll mention neutron a little bit for nuclear power, but these are the ones we're going to concentrate on. Did I tell you guys the fish story with this? So a couple years ago, a student in the class wasn't familiar with the Greek alphabet, and they were having a really, really hard time remembering alpha, beta, and gamma. And they came up with the fact that this looks like a fish, this is a bee, and then this is the dead fish. And after that, they remembered it all the time. So alpha, beta, gamma, fish, bee, and dead fish as you go through it. So these are the particles that are being released when radiation occurs. So remember, radiation is when the nucleus breaks apart and a particle is being released out. Those are the three types of particles that we're going to talk about. The first one is actually shown here on this slide. This is an alpha particle. So an alpha particle is made up of 2 protons and 2 neutrons. That means that it has a mass of 4, has 2 protons. So the symbol for that is going to be 4,2He. 4,2He. 2 protons, the mass of 4, and the 2 protons define it as a helium here. And that is released from our nucleus. So if we start out here with uranium, we're losing 2 protons, so we're going down to 90. So the element itself is changing here. And we're changing from uranium to thorium. If you look to the periodic table, thorium is number 90Th on there. And we call this the dotted particle again. Mass-wise, we've lost 4 mass here, so we take 4 away from that as well. And this is really how we keep track of what goes on in our nuclear reactions. So, for example, alpha decay. Alpha decay is when an alpha particle is released. And to draw that out, what we do is we have to write the isotope we start with. Uranium, okay, 92 protons, a mass of 238. It undergoes decay, and we get a alpha particle out plus thorium-234. So this is what we call a nuclear equation. It's showing us what's occurring as this decay occurs. And again, this is the alpha particle. Alpha particles are always the helium nucleus. So 4,2He is the symbol for an alpha particle. Yeah?
You said that's the nuclear equation for
Yep.
decaying?
Yep. So this is the nuclear equation for uranium decay. Okay. For different isotopes, you're going to have different numbers and letters, but the same general idea is there. Now, to know that it's a good equation, you have to do 2 things. You have to make sure that the mass is the same on both sides, due to the law of conservation of mass, and also the number of protons are the same. So here we've got 238 as our mass, 4 and 234 add together to be 238. We have 92 for our number of protons, 2 and 90 gives us 92. So the numbers on the top have to be the same on both sides of the arrow. The number on the bottom has to be the same. And this holds true for all nuclear equations. we can use that to make predictions as well. Let's say, for example, we have polonium-210. So polonium is number 84. This is an alpha emitter, so it's going to release 42Ag. What would the daughter particle be in that case? So on your paper, see if you can figure out what the daughter particle would be for this decay process. Okay, everyone got their ideas? Okay, so here we are. We've got a mass of 210 on our reactant side. On the product side, we've accounted for 4 of that mass. So that's going to leave us 206. Protons, we have 84. Then we have 2 accounted for. So we're going to have 82. And looking to the periodic table, PB or lead. So once you understand that you've got to keep these numbers balanced, if I give you 2 out of the 3, you can always find the third. So I could keep this out and give you the other 2, and you'd have to figure out what type of particle it is or what we're starting with if I give you the 2 products and so on. A couple of hints for you here as you go through this. Well, one major one actually. Your particle that's being released in radiation always goes after the arrow. It never goes before the arrow. So radiation is always after the arrow as far as this class is concerned. So you know that that's always going to go there. That will help you with some of the wording and so forth. So alpha particle is 42He. That. We could do the same with other particles. Here, for example, there's the uranium one drawn out. I don't know why I put that in there. Beta is the next one. Now, in beta decay, what actually occurs is an electron is released from the nucleus. And you may say to yourself, that doesn't make much sense. How is an electron released? Well, beta decay is actually the converting of a neutron to a proton plus an electron. So a neutron is changed to a proton and electron, and the electron is kicked out to the environment. So we lose one neutron and gain a proton in the process, and then the electron is kicked out as radiation. You can make sense of this if you look at the properties of a neutron. It has a mass of 1 and a charge of 0. Then you look at the proton and electron. Proton has a mass of 1, electron has a mass of 0. So that accounts for the 1 mass there of the neutron. And in terms of the charge, a proton is a +1, an electron is a -1. Add those together and you get a 0 charge overall. So you're actually still accounting for all the mass and the charge. But in this process, we've got to change from a neutron particle into 2 separate particles, one being electron and one being a proton. So the proton is what's being kicked out. And to show that, we use the symbol 0, -1e. 0 because electrons have 0 mass. -1 because an electron is basically the opposite of a neutron. And then the E just because it's an electron. As you go through it.
How do you convert a neutron to a
So it happens automatically. It's not like something that we do. Nature does it. And by saying that, I'm saying I don't know. Okay. In terms of what is happening at the most fundamental levels, I'm not sure anyone truly knows, but it is what occurs. We can see that it occurs. Okay? After the fact, we know that's what is actually occurring. Why and how it does it, I don't know. I can try and look it up, but I've tried before and I failed.
Yeah,
So.
it's not making sense to me. And I don't know how to like ask a question to,
Yeah, no, absolutely. Think of it this way. Okay. So you have your neutron, and you have the mass of your neutron, and you have a positive and negative portions of it. Okay. But when you look at it from afar, it looks like it's balanced out at zero. Because from afar, they all kind of blend together. But if you got really close, maybe you would see these different portions. Okay. Then, during the decay, the negative portion leaves, and leaves behind something, and it has a mass of 1 and a positive charge. Okay? We would call that a proton, right? Mass of 1 and a positive charge is a proton. So the part that's keeping us from defining it as a proton to start with has left, and what's behind is being called a proton. Does that help at all?
So the electron is not leaving like a shell or anything like that? Okay, so valence shells have nothing to do?
No.
Okay.
Yeah. And that's a really, really important point, actually. In nuclear reactions, we're dealing with the nucleus itself, not the electrons on the outside and so forth. And this is why different isotopes have different properties, because they'll have the same electrons and everything, and chemically they'll act the same because that's controlled by the electrons. But in terms of the isotope nucleus itself, they're different, and therefore they act different. Yeah, this one's kind of confusing for a couple of reasons. One is which is the nucleus doesn't really have an electron. Right? So how is it leaving? Well, it's being created as it does it, is the idea there. Now, once you understand the symbol, you can do exactly the same thing. For example, here, if we look at this equation with an electron, we have 14, 6 carbon. So this is carbon 14, probably the most famous of all radioactive isotopes. It releases a beta particle plus the daughter particle is actually a nitrogen atom. So again here, we have 14 for our masses on our reactant side. We have 14 on our product side. And then the number of protons is tricky because we've got a negative involved, but we got 6 here. And then negative 1 plus 7 is 6. So you have to be careful there because it's a negative to make sure that it adds up. Yeah.
Okay, so will you always get, so is the product the C?
This is the reactant.
That's a reactant. And what are those?
These two are your products.
The products. Okay. So you.
Bless you.
So you'll always have one product and one reactant, and then you have to figure out the other products, right?
Okay.
Like if you were to like ask a question, you would say,
yeah.
I have C 14, 6, and then the line with the reactant.
I've got some example problems in a minute. Perfectly fine. But to answer your question, what?
So it's like, how will we know what the product is?
So the product is after the event. So the product forms, the reaction yields this, those types of things. So the product is after. Okay? And then the starting material, or the reactant, not reactant, is the before part. So if I say carbon 14 is a beta emitter, what is the product? Or what is the daughter particle? Then you know that's going to be this.
And you said it is a what mineral? Beta, oh.
A beta emitter, which means that it's giving up beta particles.
And the beta, what did you say?
Beta particle?
Beta particle would always be E0 and then 1.
Yep.
Just like the other one you was doing was, it was
4,2
yeah,
HE. Yep.
4,2 HE.
Yeah, and they are always that. That's the key thing to remember. Yeah.
So we'll memorize what those three are, so
Mm-hmm.
in the event that obviously we get asked a question, we'll know, all right, we're looking for alpha, we're looking for beta, we're looking for gamma, and then obviously kind of algebraically plug and chug.
Yes.
Okay.
Yeah, that's the idea. Let's take a look at the last one, and then we'll do some examples, and we'll see the different types of questions. There's really 3 different types of questions I might ask, so we'll do one of each, and then we'll see where we stand. So beta, then, is always 0 minus 1e. It's an electron. So anytime you've got a beta emitter, an electron is being kicked out. The final one is gamma. Now gamma is a bit different in the fact that gamma is simply energy. Okay, this may be X-rays, this may be microwaves, this may be light. Any of these types of things is just energy. So you start out with something and you end up with the same thing, but lower in energy. So there's no actual particle, physical particle leaving. Just think of it as light leaving or energy leaving. So to describe gamma, the symbol we use is 0, 0, gamma. So there's not going to be any change with the mass, and there's not going to be any change with the number of protons. So it's also not going to change your chemical symbol. Gamma really is just describing energy loss. So that you guys are aware of it, what we do is we put a star next to the higher energy and no star next to the lower energy. So beforehand has a star, which means it has extra energy, and then it loses the star, denoting that it lost the energy. That's not something I normally ask questions about and so forth, but you may see it at some point. So I just wanted to mention it to you there. So gamma is really the boringest of all of our equations. If, for example, cobalt-60 is a gamma emitter, and I don't know that it is, but we'll just say it is. Cobalt is number 27. 0, 0 gamma plus, what would the daughter particle be? Well, it's just 60, 27. Okay, because it's 0 and 0, so there's no change as you go through it. So it's just energy there. You're not taking any protons away, neutrons away, or electrons, or anything like that. It's just, there we are. And that's the gamma one. So that's the third one.
So will they'll always be the same on both ends?
For gamma? Yeah.
Okay.
So up here at the top then is an example of it. Iodine 125 releases gamma radiation, and you get iodine 125 out. It's just the way that it goes about it. Now, one other thing I should mention with gamma, gamma rarely occurs all by itself. Most of the time, gamma radiation is paired with another form of radiation. So here, for example, is cobalt-60. Okay, cobalt-60 giving up gamma radiation and then also a beta. So in that case, it's giving up two things. It's giving up a beta and a gamma. I'm not going to ask you guys to do those or anything, but just so you know, the rules still hold true. So 60 is your mass, 0 plus, or 60 plus 0 plus 0 is 60, 27, 28 plus negative 1 is 27, plus 0 is 27. So the whole idea of balancing still holds true when you have multiple components, but it's a little more than we need to do for here. So let's try this one. Plutonium-239 decays to release an alpha particle plus what daughter particle? Let's take a minute, or probably a little less than a minute. Okay. So we start with 239 for our mass, 94 protons. We're giving up an alpha particle. So we're looking for our daughter particle here. 239 there. 4 has been accounted for so far. So this is going to be 235. 94 and 2 is going to be 92. And that's then uranium. Uranium is number 92. Does that make sense for everyone?
How are you getting, like, how are you converting this to uranium? Is that just because that's what it equals? That's the closest thing that it equals?
So here we start with 94, and then we've accounted for 2 protons, so this ends up being 92.
Okay, since that's.
So then we look to see what element has 92 protons, and that's going to be uranium. Yeah.
So then you don't go by the mass of the time?
Nope, you don't go by the mass. The identity of an element is always defined by the number of protons. And that's actually important because, like, hydrogen 3, you've got hydrogen 1, hydrogen 2, hydrogen 3. They all have different masses, but they're all hydrogen.
Okay.
And they do act differently. This is the only one that's radioactive. But that being said, they're all hydrogens. Yeah.
This may be a dumb question, but what would you have to do to your reactant to actually break that down? Like, what is actually physically happening?
To break hydrogen 3 down? Like,
No, not on that one, on the top one. Yeah.
This one?
Right.
For this to occur, it actually just occurs on its own.
Okay.
It's spontaneous. So almost all of the examples we talk about here, alpha, beta, and gamma in particular, are all spontaneous emissions. So given a certain amount of time, it will occur.
So it's like these little discs.
Now, yep. Now that amount of time may be a billionth of a second, or it may be a billion years. It differs. Every one, we'll talk about that. It's called half-life, but it will occur eventually. You can force some radioactive decays, and that's what we do in nuclear power plants. We actually force it to occur.
Speed the process.
Yeah, speed the process up, and then with that, in that case, we shoot a neutron into it and change the isotope to a radioactive one, and then that cascades down.
Oh, wow.
Goes down. It's actually really, the cascade effect is really big. I've got a slide of it later. But. Okay, let's try this one. Potassium-42. This would be what makes our bananas radioactive. Is a beta emitter. So let's see if we can figure out what the daughter particle would be in this case. Okay, everyone got their ideas? Okay, so here again, we have 42 for our mass. We've got 0 at this point, so that leaves us with 42 for our new mass. We have 19 for our number of protons and a -1. So whatever number we come up with has to be added to minus 1 to get 19. So that's going to be 20. And the symbol for that is going to be calcium. This is the hardest thing of all of these nuclear equations, is the fact that it's a negative number there. And that means that this is not 18, it's actually 20. That trips up 30% of the students on a routine basis. So I always say, once you've got it done, go back and say 20 plus a negative 1 is 19, just to double check yourself. I can't even imagine how many times I've seen students miss that for that very simple reason. I didn't make it a negative, so don't blame me. But yep, there you go. Questions about that? No? Okay. Let's try a different type here. Let's do the first one. Technetium-99 is a beta emitter. What is the daughter particle that forms in the process? Say 10, 15 seconds. Okay, so in this case, since it's not given to you as an equation, you have to figure out what goes where. Now, technetium-99 is a beta emitter, which means that technetium-99 breaks down and emits a beta particle. So technetium-99 is going to be our starting material, because that's what is being broken down. And it says that it is emitting a beta particle. So we know a beta particle is being produced, and that then leaves us with only the daughter particle defined. And in this case, it's going to be 9944. Oh, ruthenium. 9944. Everyone agree with that? Questions? Okay. So let's finish up and try the last one. What type of decay occurs when radon-226, oh shoot, I did that again. Ra-226 decays to form Rn-222? A few more seconds. Okay. Any questions before I start writing this one on the board? Okay, so with this one, the real trick is figuring out what is a reactant and what is a product. So are we starting with Ra or Rn? Ra. Because Ra is decay. It decays. So that is what is being broken apart. So that's going to be 226 Ra, 88 8. And then it's going to decay to form 22286 Rn plus 4,2 He, which is an alpha particle. Yeah.
So why is the Rn and He reversed?
It doesn't matter.
Okay.
You can do it the other way. I just did it that way because we knew this first.
Okay.
That's the only reason. Yeah, with pluses you can reorder them however you want. It makes no difference. You just can't move something from this side to this side because this is like before and after.
Okay.
So-
Okay. Yeah.
So when we're answering this on a test, do you want us to like draw a symbol, or do you want us to write it out?
Makes no difference to me. No differences to me. So the way the question is worded, you can just write alpha. And after you do some of these, you're going to be able to look at this one and know that it's just alpha, so you can just write alpha. That's perfectly fine. You could write 4,2 that'd be fine too. It really doesn't matter at all. It's, as long as you can figure out what it is, then you should be good. Any other questions? Is this stuff making sense? Yeah.
Can you do one? I know you said it was one, but can you do one like gamma decay?
Oh, of course. Of course. I don't think it's boring, but that's just me. I'm kind of a special case. Okay, so the wording of something for a gamma decay would be like, I'm just going to make something up here. So actually, let me change one. I don't like the element. I'd rather have isotope there. Okay. What isotope will decay to form chlorine-40 through gamma decay? So on your paper, write out an equation for this. Okay, so the equation for this is going to be, we know that we're making gamma, so that's going to be 0, 0, and this, and we're also forming 40, 17Cl. So what isotope will decay to form that? Well, 40 plus 0 is going to be 40, 17 plus 0 is 17, which is also Cl. So the isotope that will decay to form chlorine-40 through gamma decay is chlorine-40. Yep. Yeah, it's going to always be like that. Because it's 0, 0, so nothing's going to change as you go through it. But I'm glad you asked, because that gave me a chance to have a question where you need to find the starting one. Okay, any other questions? Okay, so that's how we describe nuclear equations and keeping track of things. So if you know, for example, what the daughter particle is and the type of radiation, you can figure out what the starting isotope is. If you know the starting isotope and the type of radiation, you can find the daughter particle. given 2 out of the 3, you can always find the third. And that's kind of the approach we'll take. Now there are a few other types of radiation, as I mentioned. You may see them from time to time. We're not going to talk about them at all. Positron emission gives off what's called a positron. It's the opposite of an electron. Don't worry about it. And electron capture is another one. The final one that we will mention briefly a little bit later on is neutron. And in that case, you're using a neutron to actually cause radiation decay and so forth. And we'll talk about that because that's what happens in nuclear power plants and nuclear weapons, actually. We'll talk about those later on. Yeah?
Okay, I'm still like caught on the beta emission.
Yeah.
So is a neutron itself like 2 different things? Like a positive and a negative thing put together? And so whenever it like releases
No,
no?
not
Okay,
really.
sorry.
No, it's fine. You're thinking about it, but the problem is this. In chemistry, we have, for historical reasons, but also for practical reasons, defined the most basic particles as a proton, neutron, electron. And we treat them as if they are the thing. But that is not actually true. So protons, neutrons, electrons are made up of other things called subatomic particles, other types of subatomic particles. You may have heard of some of them like neutrinos, quarks, leptons, neutrinos. I said that twice. But there are several of them that make it up. Now in chemistry, we don't deal with those because the fundamental properties of elements are not directly affected by them. They're made up of them as you go up the scale, but you don't have to go back down to them to understand it. Now, a neutron is not one thing. Okay? It's actually made up of these smaller things, and I'm sure the answer to your question has to do with the smaller things in some degree, but honestly, I'm not sure anyone really knows.
Right. It just like, it doesn't make sense to me, and it's really
It bothers you, I can
like
tell.
why does losing an electron give you a proton?
Well, losing the properties of an electron
Yeah.
gives you the properties of a proton.
So it's
Maybe a better way to think of it.
yeah. Okay. So it's just the properties that are changed. No. Never mind.
No.
It's I know it's so frustrating. I just don't know how to ask.
No.
question.
Okay, however you ask, I'm not going to be able to answer it. Okay? Because I completely understand your issue here.
Okay.
The way I think of it is this. If you have yellow and blue overlapping, you have green, right?
Yeah.
Take the yellow away, what color do you have? Blue. Okay?
Okay.
Now, when they're overlapping like that, we call it green. But the green is actually made up of 2 different components. Like a neutron is made up of different components. Take one of those components away and you're left with something, and we just call it something else. Now, scientifically, that's not 100% correct in any way, shape, or form, but that's the way I've come to think of it.
Okay. Yeah, that helps for sure.
Okay, so that is how we describe reactions that occur. There are a few other properties that we need to discuss to understand our practical applications and so forth. And the first of these is half-life. So half-life is the rate at which materials decay. So all of these types of radiations are spontaneous decays, and that means they're just going to occur over time, but the speed at which they decay is different for every isotope. It's characteristic for that isotope. One isotope will always decay at the same rate, but isotope to isotope, they're going to have very, very differing rates. So for example, technetium, which is used in medical applications, has a half-life of 6 hours. So if a doctor wants to use it, he has to call and have the technetium sent to him per use. He can't just keep it in a stockroom because over a day, a lot of your material has decayed away to unuseful stuff. On the other hand, uranium-235 has a half-life of 7 times 10 to the 8th years. So I think that's in the billions. of years there. So radioactive waste actually contains some uranium-235. So if we want to wait until all of the radioactive waste is going to decay, it's going to be in the hundreds of billions of years, actually, as it goes through it. So each isotope then has a different time period. And because of those time periods, you can do different things with it. Tritium, for example, is 12 years. The radioactive dating that tritium does is in wines. So if you buy like super, super old, expensive wines, and I'm not in this world at all, so don't pretend like I am, where you're paying tens of thousands of dollars or millions of dollars for bottles of wine, one of the things they'll do is they sample the air on the inside of the bottle, they draw some of the air out, and then they look at how much tritium is in there. And from that, you can actually figure out how old a bottle of wine is. Because when it's capped, the tritium is trapped in there, and then, or corked. The tritium is trapped in there and it can't get out. So there's all different types of things and practical applications, but to understand it, you have to understand half-life. Now, we are going to take a very simplistic approach to half-life, and it is simply in the definition itself. In the amount of time of a half-life, half of your material will decay. So if I start with 100 grams of something, after one half-life, half of that is going to disappear. So now I'm going to have 50 grams. So half of it disappears. Then, if I wait one more half-life, half of that amount's going to disappear. So now I'm down to 25 grams. And it gets cut in half every time. So one more half-life is going to be 12.5 grams, and so forth and so on. So every half-life you have, the amount is halved as you go through. Now, this half-life is different time periods. Let's say, for example, that it is, well, technetium, it makes a nice one. That means that going from 100 grams to 50 grams is about 6 hours. Going from 50 grams to 25 grams is also 6 hours. So if you want a 100 gram sample to decay to 25, that's going to be 12 hours. 12 hours. It's going to be 2 half-lives, where the half-life is defined as 6 hours.
So is that a given for all isotopes, or for the half-lives?
All isotopes, the half-lives act exactly the same. The only difference is the amount of time that a half-life is.
Okay.
And the half-life time is not something that you're ever going to know. It's always going to have to be given to you because it's literally different for everyone.
Okay.
So you don't need to know like what isotopes are radioactive, and also you don't need to know the half-lives of them and so forth. It's going to be given to you. Or everything else is going to be given to you for you to figure out what the half-life is. Okay, let's try a problem once. How many half-lives have passed if a 400 gram sample decays to 25 grams? Okay, everyone got their ideas? Okay. So I'm going to start with 400 grams. One half-life is going to take me down to 200 grams. Another is going to take me to 100 grams, to 50 grams, to 25 grams. So it's going to take 1, 2, 3, 4 half-lives. 4 half-lives to get down to 25 grams. Questions about that? Okay, now this is the way that we are going to do it as a class. There's a couple things you need to know about this. This works when you have whole number half-lives. So 1 half-life, 2 half-lives, 3 half-lives. It doesn't work if you have 3.5 half-lives. 3.25 half-lives or whatever. So we will only work with whole number half-lives in this class. Everything will work out perfectly. Also, because of that, you do not need the mathematical explanation of half-lives more than just dividing by 2 or multiplying by 2. If you look online and so forth, there is a mathematical equation you can use to calculate half-lives and so forth. We are not doing that in this class. If you want to use it, by all means, please feel free. It works perfectly fine, but we're not getting into the math of that at all. Okay, so we can just divide or multiply by 2. Okay, everyone good with this one? Okay, let's see what would happen if I change this to say how many days have passed if a 400 gram sample decays to 25 grams and the half-life is 3 days.
To get to 25?
To get to 25 grams again.
Oh, okay. So you would consider one day as going to 200?
Well, that is 1 half-life.
Well, I mean, yeah, 1 half-life.
1 half-life. Yep, which is how long? Not 1 day. It's
1 hour. No, 6 hours.
3 days.
3 days.
Oh,
3 days in this problem. And a half-life is 6 hours. 3 days, yeah. 6 hours corresponds to the technetium.
Oh, I didn't see what says half-life. Okay.
And a half-life is 3 days.
What is that after 25 grams? That's just the,
There you go. Better.
okay.
That was the cross out of the old question mark. Any other? Okay, so to do this problem, we first figure out how many half-lives it's going to take to get down to 25 grams, and that's 4. So 4 half-lives, and if each half-life is 3 days, you multiply the 2 together, and 12 days would pass. 12 days would pass. Okay. So when it asks for a time period like this, just figure out how many half-lives have passed, and then how long each half-life is. Now this is very, very, very common in carbon dating. So one of the primary things is carbon-14 here is used in carbon dating. So they figure out how much carbon has decayed down, and then from that they can figure out how long ago the sample was taken, or how long ago the tree was burned, or the cotton was woven, or things like that.
So would that be the same if you asked a question on how many hours?
Yep.
Okay.
So how many hours? In this case, you would have to take the 12 days times 24 hours. But if the half-life was already in hours, it would just be a multiply.
Okay.
Years would be the same too. So, let's do one more problem. Going the other direction. Or just my brain just How large was a starting sample if 40 grams remains after 6 half-lives? So how large was the starting sample if 40 grams remains after 6 half-lives? Okay, everyone got their ideas? A few people punching it out still, but okay. So if 40 grams remains after 6 half-lives, we have to go backwards in time. So instead of dividing by 2, we're going to double it. So if we go back 1 half-life, it would have had 80 grams. The second half-life would be 160. The third would be 320. This is getting kind of crazy, I guess. You need to pick a smaller number. 640, 1280, 1560? No, 2560. 5, 6. So 2,560 grams would have been your starting sample size. So here, when you're going backwards in time, you're actually multiplying by 2 instead of dividing by 2. Okay, one more and then we'll give up for the day. The last one here. How long has passed, I should say if an isotope with a half-life of 2 days has decayed to 25% remaining? Just to make sure everyone's getting started, you're going to start out with 100% and then figure out how long it's taken to get down to 25%. So to run through this, we're going to start out at 100%. We need to figure out how many half-lives have passed to get down to 25%. Well, the first half-life is going to take us to 50%. The second half-life will then take us to 25%. So 2 half-lives have passed. If each half-life is 2 days, that means 4 days have gone by. So 4 days would be how long it's taken. Good? You guys are all packing up. I assume it's good. Okay. Go. Enjoy your weekend. The last weekend before Thanksgiving, I think. Thanksgiving's next week, right? Yep. Already? Yep. Mashed potatoes.
We have an exam the week after Thanksgiving. Right?
Yes.
Okay.
Yes. The Tuesday after Thanksgiving.
Okay.
Oh wait, is that right? Or is it the next week? I think it's one more week. So after Thanksgiving, we do not have an exam. It's the week after it.
Okay. So the first week of Thanksgiving.
First week of December. December 6th is what it would be for this class. We have 3 more lectures. So 1 next week and then 2 the week after Thanksgiving.
So are we gonna get to chapter 8?
So,
Okay.
I'm not, chapter 8, I'm not certain, but I'm not gonna start a new chapter with only one lecture left. Or
Okay.
something like that, so we'll have to see. I really don't think we will. Yeah. Hey, what's up?
This, the final exam.
It is. Yep. Yep. Use your old exams to study for. Cool.
Have a good day.
Yeah, you too. See you later. I'm gonna hit the lights, everyone.